Alright, it is time for today's daily LeetCode challenge. It is the first day of February. We are entering the new month. I did the full 31-day challenge for January, which is good. Now we're going to embark on a new month. It's Monday, so hopefully the question is not too hard. Let's take a look. Number of 1 bits. Whatever that means. Alright, let's see. Oh, write a function that takes an unsigned integer and it returns the number of 1 bits it has, also known as the Hamming weight. So, I think can be done in Python with one line. Non-signed, blah blah blah. It will be given as a signed integer type. Java is all about Java. Signed integer. How would you optimize it? Well, let's not look at the follow-up right now. I mean, in Python, it's very easy to turn integers into binaries with arbitrary number of digits. I might have actually known the exact function to do that, but before we do it, we need to make a new directory. See, we're gonna do 2021 and this. Now we're gonna copy our template into our challenge for February. This as well. We have to make changes here, so it's gonna be February. Yeah, I think they threw a easy ball today. LeetCode, at least for Python, in a more or less cheating kind of way, because I'm pretty sure the official way will be very different. Will be, to actually go through the numbers and find how many ones in there. I mean, it's all right. Let's just take a look, see if my understanding of it is right. Let's say given an integer. I don't even know what this integer is. What is this? That's oh, come on, you know this. This is 8. 8 is it 11? That's 11. So a equals 11. Let's try. I think it's format a, and then we call it a, turn it into binary with 32 with where do I put 0 b? No, 32. Oh, no. This is just 32 emptiness, right? It's the same. It's 320. Okay, 32 is this. I think 0 is here. It's not. Where do we put 0? 0, 3, 2? There we go. 0, 3, 2. So what we need to do is this dot, I think there's a count. Count 1. That's 3. I think that is the solution. Yeah, I cannot copy. I don't know why I cannot copy. Let's go back here. So we're gonna return format n. We do 0, 32, 0, binary dot count 1. And let's take a look at this. Oh my dear Lord. Alright, I probably don't even want to. Which we on this? 1, 2, 3, 4, 5, 6, 7. 2 to the 7. Is that 128? Calculator out 2 to the 7. Yeah, it's 128. Which means the input, if it's 11, we're going to get 3. If it's 128, we're going to get 1. This is some value, and I don't want to really worry about that value, so I'm not going to do that. just test these two. Most likely it's going to be correct. Name S is not defined because I never defined it in the first place. And we pass, so we just return this, it will work. Probably work pretty fast as well. Judging accepted, yep. Oh, look at the runtime. Are you saying that there's a better way? Gotta be a better way. Alright, so I'm gonna say this is a more or less cheating method because I used Python's built-in function to convert input into binary string into binary and then literally count the number of ones. So it runs at 52. Yeah, it's not like time complexity. It's almost it's 01, right? It's 01. So I'm not going to write that. So just say 52 milliseconds, and then we are ranking at a very poor 5%. This is bonkers. 5%. All right, I'll try to see if we can find other ways. Some bit manipulation for sure, right? So given a number, you need to know how many ones there are. Well, the maximum is 32. Let's see. It doesn't have to be that many. Just say 0, 0, 0, 0, 1, 0, 1, 1. All right, let's do this. See if there are other methods we can come up with. Usually would involve some like 2's complement, something like that, or some type of mask. If we like do ones, right? So if we say exclusive or 1, then we get 1, 1, 1, 1, 0, 1, 0, 0. Right? So all the 1s become 0, all the 0 become 1. What does this tell us? Well, this tells us, it doesn't tell us anything. I mean, it's slow. What, like, I mean, I can actually do it, just like divided by 2, divided by 2, divided by 2. Not divided by 2, just shifting. Yeah, we can shift. We can shift. We end it with 1. So we can shift and end it with 1. So let's take 32 times. Let's try it. I mean, it's could be faster. Alright, so we just going to shift. Say while n count 0, while n count plus equal to n and 1. Right, and then n 1. Turn count. Let's see if it works. Pass as well. Alright, so basically we just, okay, I'm not going to explain right now because this might be wrong. Just gonna do it. See if it passes. Pass. How about your runtime? All right. Click too fast. It hasn't even calculated yet. One more time. Oh, I think that is the solution. Let's see what's the majority. Yeah, it's the same way, same method, exact same method. Okay, so this is the. Okay, this seems to be the common method. We simply right shift a given number, and each time we check whether the shifted off value is a 1. If it is, we increment the counter. That's it. So this one gives us 32 milliseconds, and that is 63% ranking, which is decent. Yeah, I know what you're thinking. Do you know what I'm thinking? I'm thinking if it's possible to turn this into a one-liner, but probably not. I mean, we can, because we know how many times we're going to shift. It's going to be shift 32 times. So every time it could be this and 1. How do you perform 2? Yeah, let's just stop here. It's not gonna be readable. Yeah, this is good enough. Let's take a look. And also take a look at solving, like, what does this mean? If this function is called many times, how would you optimize it? So many times, what do you mean by many times? Oh, many times? That's probably not a good solution. Well, 32. It's a signed, hold on, unsigned integer. So it's unsigned. And it says has 32. So the maximum number that you can have for 32 is 2 to the 31, right? 2 to the 32. Yeah, it's 2 to the 32. I think that's the maximum number of. So this is the max number you can have for a signed integer, for an unsigned integer, 2 to the 32. So that will be, each integer is 4 bytes, right? Times 4 bytes, and kilobytes, megabytes. Ooh, 16 gigabytes to store everything. That seems excessive. I was thinking about creating mapping. I mean, we can definitely map it, right? We can every time you hit it, you map it. If you hit it, you map it, and then if there's any repeat, so you can just go to the map. Oh, it's actually no, because a lot of the numbers will have the same. Probably not. No, I want to see how is this resolved. Optimize it. It's an easy question, no doubt about it. Yeah, we had an easy one today. Yeah, I'll leave a like. Loop and a flip. Again, bitmask. Oh, they use a bitmask. It's the same idea. Bit manipulation. flip the least significant 1 bit. It's the number to 0 and add 1 to the sum. Doing a bitwise AND of n and n per minus 1 flips the least significant 1 bit n minus 1, because this one would be 1. I borrow it until this one gets borrowed, so this becomes 0. Remains the same. So if we AND, then if we AND it, then this will become 0, but the rest is the same. Yeah, that does make sense. Therefore, always flip the least bit. Why was it not 0? So we just flip it, flip. Oh, that is very smart. Oh, wow. This is even better. Yeah, you don't even have to do format. You just do this. You're being stupid, man. I bet it might be even faster. Let's try. Yeah, bin is sufficient. Bin is sufficient. See, I told you, bin is sufficient. This is, yeah, I know why. It's because this is so stupid. If I format it, I was looking at it, it says 32 bits, or I just get all 32 bits out, but you don't have to. You don't have to count all the zeros. I don't understand why it happened to me. Alright, I'm gonna leave this. This is a sign of dumbness, and this is the sign of enlightenment. Unbelievable. Solution 1 was dumb. There is no need to fill the entire 32 bits. We can just use bin function, binary function, and it will work. So this gives us 32 milliseconds, 36 milliseconds. Much better. 26%. Okay, so instead of say format, it's also shorter. Bin n, boom, done. End of the story. But I like the manipulation one. That's so. I mean, from this one included, I learned 2-bit manipulation. Right. Not sure if I can really memorize these, but the first one is a few days ago when we're trying to divide an even number by 2 repeatedly until it reaches an odd number. So that's the first one. I'm actually talk about it later. But this one is also very interesting. That is to find, well, not necessarily to find, to flip the last digit, that is 1, to flip that into a 0. So all we need to do is we set up a counter, and we say while n, and counter will plus equal 1, and then n will equal to n and n minus 1. I will return counter. I believe this one is correct. Yep. I think this one will probably be the fastest. Oh, psh, bad. Should have tested it first. Oh, it's all right. Yeah, I mean it's fine. At this point, it doesn't matter. But it's just the solution is genius. I can say this is one of the official solutions. Its genius lies in the bit manipulation, where the rightmost one digit gets flipped to 0 by a simple operation, n and n minus 1. Yeah, that's really smart. Yeah, that's really smart. And n minus 1, because n minus 1, it will always, if the last digit is 1, that will turn. If it's not, you're going to borrow until the rightmost 1, and then turn that into a 0 when you minus 1, and you end the 2, and then that will be flipped. Yeah, it's pretty smart. All right, that's actually it for this question. Now we got an easy one, and we went through it without sweat. But at this point, I actually want to talk about the other method. So the idea is, say we have a, let's say, equals, which number I'm thinking about? 20, right? A is 20, and then we want to just keep dividing a by 2 until we get an odd number. Now the easy way to do is just, so while a is even, then we say a divided by 2, and then a is 5. Right? That's the generic way of doing it. However, there is a smarter way that LeetCode 215 has mentioned. I think it's a divided by a and minus a. That's 5. It's like one math function, and it immediately turns into the target. Now if we're looking at, let's look at the bin 20. So this is 20. So it's 1 0. So it's 1 0 1 0 0, right? So what happens if we do minus a? Now we know minus is represented by 2's complement. So if we do bin minus a, it's going to be the complement. So it's going to be a bunch of 1's, and then a bunch of 1's, and then 0 1 0 1 1, right? And then we're going to plus 1, so it's going to be a bunch of 1's, 0 1 1 0 0, right? Let's just take a look. Minus 20. All right, this is not what I had expected. This is not what I had expected. All right, let's do 8. So 8, so 0 8b. All right, and then let's do minus 20. Please show me the. Oh my dear Lord, this is not smart. All right, it's 2's complement. All right, 2's complement. So we can actually do this. I think it's going to be this. Yeah, it's going to be this plus 1. Actually, I'm not confident. I think this is going to return to me the minus. That's the bull crap. This is bull crap. Anyway, so we have. Yeah, I'm not even want to do it here. Anyway, we have. Let's say we have a 0 0 0 1 0 1 0, right? This This is 20. So the 2's complement is this one. We're gonna plus 1. So I'm gonna do the reverse first. So it's gonna be this 0, 1, 0, 1, 0, 1, 1. Right? So we're gonna reverse it, and then it's gonna plus 1, which becomes 0, 0, 1. So you're looking at these two, right? What you can see is before this 1, 0, 0, everything will be, if we AND these two numbers, everything will become 0. And the only thing left is the 1, 0, 0. So the only thing left after the operation of, let's see if A is 220. After the operation of A and minus A, the only thing left will be the largest factor, that is the power of 2, right? The largest factor that is power of 2 relative to this number. So the largest, so which means the value, the rightmost one, and along with its trailing zeros. So this one should give us 4. This one gives us a 4. So when we do the division, it becomes 5. So we just remove this, and then it becomes 5. We remove the trailing zeros, and we turn it into the first odd number. So this is just very ingenious way of using AND. And today we learned something also ingenious. It's this one, AND the value minus 1 to flip the bit of the rightmost ones. So in a sense, the LeetCode is good to me in this sense. Just you read through people's comments and you read through solutions and kind of broaden your horizon, kind of just give you more appreciation of these tiny tricks. I mean, is this going to be really helpful for interviews? Maybe, maybe not. You can definitely do this question this way. I don't think anybody will have any problem. Or they're like, what if I don't know Python? And you can always do it this way, right? It's fine. But to learn, to understand that there are always these type of tricks that exist, it's useful to me. And I have actually uncovered a lot of interesting things about Python, like bisect, right? The binary search in Python, right? In the past, I always read it myself, and writing binary search by yourself is not trivial. There are edge cases and stuff that if you're not familiar with it, or you don't have a formula already memorized, it's going to be tricky. And then after I learned that Python actually has implementation of binary search via bisect, it's just opened my mind, right? That's opened my mind. And another thing that opens my mind with Python is what's that? The cache, LRU cache. Last recently used cache. It's very helpful for me, to write DP solutions without creating my cache manually. I mean, this method sometimes works, sometimes it does not, because it records only, it caches the arguments as the keys. So the arguments has to be hashable. So it's not like useful every single time, but it's something good to know. So just like these little bits, just by doing LeetCode, it helps you appreciate the language more, appreciate these tricks more. Anyway, let's take a look at any potential solutions, see if there's anything interesting. So this one is, that's actually also good. Yep, this is the same thing. This is oh no, this is not the same thing. This is just shifting. Yeah, this is shifting. Okay, this is the other one. This is the official solution. Yeah, that's true. What's the intuition behind this? I will be hesitant to say there's an intuition. It's just some people think that this will be a better way, and they're trying to see if there is an easy way to flip the last one bit, and then they find out that it is actually possible. Ooh, recursion. I think recursion is necessary for this one. What is intuition? Intuition is just, yeah, that's the intuition. Like, brilliant, genius. Even faster. Just 5 operations. Counting number 1, yeah. Classical bit manipulation trick. This person's good as well. Babichev. Remember, and we'll remove the rightmost in binary representation. Yeah, complexity 01 for sure. It's always going to be 01. Just 5 operations. Oh. Yeah, interval will be okay with that. I doubt if he will be really happy, but okay, let's see. Huh. We'll count number of non-zero bits in each pair. That's true. We have 2, 0, 1, 1, 1, and the oh, 1, 1. Huh. Now the second step. First 8 bits. That is 1100, 1100. Number of non-zero bits in groups of 4. So we have 1, 1, 0, 0. Hold on. How it become 110? It says 1100 and wait a second. We will do this. Isn't that 1100? And we're doing shifting. Hold on. I understand this, right? This is good. You have 2, like 1, 0, 1, 0, and then that's that. And this one plus right shift 1 and doing the same thing. This I do not understand. I do not understand. Number of non-zero bits in groups of 4 will be computed. We stopped on number 1, 0, 0, 0, 0, 0, yeah. Now we have, this is not what we have. 0, 0, 1, 0. No, where does this 1, 0 come from? If it's a 1, it would be 0, 1, 0, 0. It should be 0, 1, 0, 0, 0. Then 0, 1, 0, 0. And this is definitely not the same as this one. We shift to the right. Geez, we shift to the right. And we end this. I don't, deal with even and odd bits. Count the number of non-zero bits in each pair. Alright, I don't think this makes any sense. Or it might not make any sense. I choose n as 1, 1, 0, 0, 0, 1, 1, 0. And if I do this, I get this. Alright, why don't you just write it out? Let's just take a look. You know, I know you're very suspicious, which is always good. Nah, I don't think this one will I'll actually include this one, but I'm curious. Very curious what this one can do. But I need to first understand what this number is. Probably give me a, yeah, let's see. I think should be fun. If I do int, yes, int 2, 198. So bin 198, let's see if it's what we expect. Yeah, that's 198. Let's do, I don't need all these. So we have 198 and what's the number? 1, 2, 3, 4. It's only 4, right? And let's just check. It passed. I'm sure it passed. I want to see. I want to print. Yeah, I want to print this. Man, it'll be very tough to do this. So this, I want to do a binary on this, and then I want to print binary this. Well, you have to realize that the n has changed, so these two has to be here, and then we need to print out binary n, right, like this. All right. What is this? All right, I don't like this. I need a format because I want to dictate how many zeros, how many leading zeros this can be. Yeah, otherwise it will be a little bit difficult to determine what actually happened. So instead of doing binary, we just use format. Format, and we do 08b. All right, let's see. So this is what we do. Oh, we probably shouldn't use 0. Probably should be 32 because everything will be 32. Everything is with 0, so it doesn't really matter. 1, 2, 3, 4, 5, 6, 7. Yeah, 8 should be sufficient. 8 should be sufficient. All right, so it does not look like this at all. It does not look like this. It says it's going to be here. But this one and here, it gave me 0, 1, 0, 0, 0, and 1, 0, 0. That doesn't make any sense. 0, 1, 0. Oh, it does make sense. Hold on. It didn't say, did it say it's end? First line will count the number. Just say we'll count the number. But that's also not. Oh, that is correct. It does count the number. Oh my god. Oh, it's not this line alone. It's not this command alone. It's the entire thing. The entire thing count the number of ones. Oops, the entire thing. Now, what is the intuition in this one? I don't know what the intuition is, but we start with this, and then this one we end with this, which will we get? So we'll have 0, 1, 0, 1, 0, 1, and 0, 1. So we get the one that's in the odd position. And then we right shift 1, so we get the ones on the even position. And we add them together. So we get it on the odd position, and we right shift 1, and then we get it on the even position. And then we add them together, and that's the number of ones in each of the two positions. Okay, that's good. And then we are going to do a 1, 1, 0, 0, 1, 1, 0, 0. So we're gonna run it first. So we know that we have 2 in the first 2. So we need to know how many is in this. It will be slightly different. All right. So we do it first. So we know that there are this many in this position, right? And then they're gonna be 1 in this position, and then we're gonna shift 2 times. So we checked on the first 2. Now I check on the second 2. So I check on the second 2. When we check on the first 2, we get a 1, 0 here, which means we know they're gonna be 2. And then we check on the second one, which gives us a 0. So we have 0, and one second one, we check there is a 1. So when I add them together, so that will be the first 4, right? We have the first 4, we have 2, and the second 4 we also have 2. But why is it the 1 is in this position? If we do an AND right here, this will give us, I don't, hold on, I might not get this right, which means I want to take a closer look. So we do our 3s, what is it? What is it? It's 0, 0, 1, 0, 0, 0, 1, 0. 0, 0, 1, 0, 0, 0, 1, 0. That is correct. So the first one will give us all 0 and 1. Really? Oh, I think it is. This is wrong. You cannot look at the first 8, I think. You have to look at the last 8. It's this. You have to look at the last 8. Yeah, 0, 0, 1, 1, 0, 0, 1, 1. So we always consider on the smaller side. So we know that in these two positions, if it's 1 or 2, so it's 1 is going to be this, and the 2 is going to be this. So we identify it's going to be 1, and then we are shifting. So we're shifting this to the right. So, but this one is still not caught. Oh, my bad. Shift 2. Yeah, it's shift 2. Shift 2. So we shift 2. So this one comes here. So we can record a 2 here. And we also record another 1. So add it together. It's going to be 2. Yeah, so this is not correct. I need to mention it. And then we shift 4 times. So we combine the first 4. Now this is already the first 4. So first 4, 2, second 4 is also 2. And then shift 4 times would be first 8. And then the second 8. Right? First 8 and second 8. And then first 16, second 16, first 32, second 32. Wow. All right. This one is pretty brilliant. All right. First of all, how do I? There is a typo. It shouldn't be first. How does that feel? First 8. First 8-bit. Yeah. Great solution. The second one is. However, there is a typo in your second step. You said first 8-bit is 11001100. But it should be 00110011. Yeah. I still give him a vote. All right, this is just genius. All right, this is just genius. Let me use an example to explain. Given n equals 198, which is what? Which is 110011001110. Right, 11001110. And consider only the least significant 8 bits. N and this equals 11000110 and 01010101 equals so equals 0100, and then this one will be 0100. This means we have 2. Now we have 1. We have 1 in the leftmost 2 bits, and another 1 in the mid leftmost 2 bits. N1 and this equals 0, 1, 1, 0, 0, 0, 1, 1, and 0, 1, 0, 1, 0, 1, 0, 1 equals 0, 1, 0, 0, 0, 0, 0, 1. Alright, this means are you sure? Feel like is it not right shift 1? Yeah. Right shift 1 we have 0, 1. This is 0, 0, 0, 0, 1. Yeah, this means we have this means we have 1, 1 again in the, we have another 1 in the leftmost 2 bits, and a 1 and a 1, 1 in the rightmost 2 bits. Combine the two results. Combine the two results, which means 0, 1, 0, 0, 0, 1, 0, 0 plus 0, 1, 0, 0, 0, 0, 0, 1 equals 1, 0, 1, 0, 0, 1, 0, 0, 0, and then 1, 0, 0, 0, 0, 1, 0, 1. This means we have 2 1s in the leftmost 2 bits, 1 1 in the middle 2 bits, and another 1 1 in the rightmost 2 bits. We proceed to use mask which aggregates the number of 1s in the first 4 bits and last 4 bits. Similarly, we use this mask for aggregating the first 8 bits. This for the first 16 bits, and this for the first 32 bits. This operation runs in 5 steps for all 32-bit numbers. Genius. Let's try it. I don't think it'll be any faster, but could be. Doesn't matter, but this is smart. This is very smart. All right. That's it for today. Enough exploration, and I'm not sure if I will actually be able to memorize this. This is just too magical to me. But it's good to know. It's good to know. All right, that's it for today, and we'll talk tomorrow. Done.